Hey everyone, so this is the 13th video on lenses and optical instruments. So we're basically going to continue our discussion with mirrors and talk about how they're going to affect with lenses. Basically shifting from the concept of reflection, and we're now going to talk about refraction. Um, so if you didn't know, most of the things that we use lenses for, besides actually seeing stuff, are the typical optical instruments like um, telescopes and microscopes and things like that. Now, here there are just like there are two different mirrors, we have two different lenses. So one type of lens that we're going to talk about is the double convex lens, and then the other one's the double concave lens. So once again, we're bringing those terms back. But some of the things that we've talked about with convex mirrors don't do the same thing with convex lenses. And that's going to be an important thing to note. Now, there are other types, like there are these where it's a plano-convex lens where one side is flat, the other side is convex, and then we have one of these convex meniscus ones where you almost have like a convex and a concave next to each other, and then same thing here. So there are other types, but we're pretty much going to be focusing on the double ones. In fact, I'm just going to call this a regular convex lens and a concave. Or, like I said, I tend to skip this and actually call it straight a converging lens instead, and this being a diverging lens. So, again, that's one of the reasons why I kind of don't call these as convex and concave, because everything that we talk about with concave mirrors and how concave mirrors were converging mirrors, it turns out that concave lenses are diverging lenses. So it kind of gets flipped. So to me, it's just easier to kind of say all converging mirrors and lenses act one way and all diverging mirrors and lenses act another, as opposed to remembering which one's which. Um, so just like how with the mirror, one of the things that we're going to want to do is create ray diagrams in order to figure out, where things are going to land. Now, the type of lens that we're going to deal with are thin lenses. We're going to pretty much assume that they have very little thickness, and all it is that they have that shape that allows for this special, unique refraction property. Um, Now, it turns out that just like with the mirrors, we end up getting a very similar thing happening where when light rays are coming from the sun or infinitely far away and come parallel to the principal axis, they'll end up converging their light into a certain point. So all the lines will converge at the focal point. However, um, there's a little bit more going on than with the mirrors. In particular, where that focal point is a little bit different. So, first, I don't have it on here, but there's actually two focal points. There's a focal point on the left side and a focal point on the right side, mainly because of the fact that there is a focal point caused by this convex lens and this convex lens. So both of these are actually uh, have their own focal point. Um, this is what I was saying before about the with the mirror was that when the lines are coming parallel to the principal axis, like pretty much, uh, I don't want to say perpendicular to the lens, but straight on with the lens, the point, all the lines will end up converging at the focal point along the principal axis. But if it comes in at an angle, then it will end up coming in and the focal point will actually shift down. So a lot of times, instead of calling it a focal point, they sometimes call it a focal plane because technically these lines coming from infinitely far away, parallel lines, will focus at any point along this axis, this plane, depending on how the lines are angled. So then this is what the diverging one is. So again, with the converging, they're going to come in and then refract towards the focal point. Here, the lines will come in and they're going to diverge outwards, um, not crossing. But if we backtrack all those lines, it would look as if they originated from the focal point on this side. So again, the rays kind of do the same thing. Um, Now, with optometrists, a lot of people who actually deal with things with lenses, instead of talking about the focal point, what they'll talk about instead is the power of the lens. The power of the lens is defined as the inverse of the focal length, essentially. The unit for the power lens is actually it's measured in diopter, so you'll see that, and it's technically inverse meters. Now, the ray tracing is almost exactly like the mirror, which is nice because you don't have to memorize anything else. There is slight differences though. Like for example, we still have the one ray coming parallel and then through the focal point, but it doesn't get bounced back because remember this isn't a mirror. It's not reflecting. It's transmitting through. It's refracting. So you're going to have one line that goes parallel and then through the focal point. You're going to have your second line through the focal point and then parallel. And then the third line just goes straight through the middle. And again, where all three lines pass, that's where we end up getting our image shown. Uh, and then a similar thing for the diverging lens, where we go parallel and then it's going to refract outward, but it's going to do that as if it came from the focal point. So you kind of have to backtrack it too. Um, Same thing, a line that looks like it's going to be going through this focal point, then goes parallel. We have to then backtrack it, and then one through the center. You can almost think of this as being like almost like a mirror, where um, if you kind of treated it like that, you would sort of get the similar result. The only difference is you'd have to make sure that the line that's going through the focal point isn't going through this one, it's going through the other side. All right, now the sign conventions here are a little bit different. So first, the focal length sign conventions are the same, positive for converging, minus for diverging. This is again one of the reasons why I ignore the concave and convex terminology, because concave mirrors have a positive focal length, but concave lenses have a negative focal length. So it gets a little bit confusing there with that switch. So here, just remember converging positive, diverging negative. Object distance, now there actually is a little bit of a caveat. With the mirrors, it was always positive. There was no way that you could get an object distance that was negative. But for the mirrors, for lenses, it is actually possible to get a negative object distance. However, that's only going to occur when we deal with combination lenses. So when you're dealing with single lenses, you're never going to have an object distance that's not positive. But the object distance is positive if it comes on the side of the lens that where the light's coming from. So for the most part, typically when we draw these diagrams, we're always drawing things on the starting at the left, because that's how we read left to right. So a lot of times the left side of the lens is going to be defined as positive because light's going to come from this direction towards here. Like I said though, when it comes to combination lenses, that's the only time you may see a case where where the object is actually formed on the other side. Image distance. Now, this one's a little bit different, mainly because of the difference in the purpose. The purpose of a mirror was to reflect light. So the image distance was positive if the light basically got reflected and an image was formed on the real world side, so where the object came from. Because a lens, the purpose of the lens is actually to transmit, and allow light to travel through it, well, we define the image distance as being positive if it occurs on the opposite side of the lens. So here, if the object is on the left side, uh, if the image is formed on the right side, on the opposite side, we would give this a positive distance because that's where it should be. If that kind of makes sense, that's how I think of it. Is that it's strictly based off of the purpose of a lens being different than a mirror. Mirror wants to reflect the light, while lenses transmit the light. The image height is the same. Positive up means upright, negative means inverted. Now it turns out if we do similar constructions of calculations and setups, we'll actually find a similar relationship. So it turns out that the mirror equation that we were using last time is once again used for the lens. So it's a really nice thing that we can do. In fact, you're going to notice this when we talk about when we continue our discussion about some of the other properties of light and some of the unique phenomena that we're going to be able to experience. That the things that we're going to talk about in the next two, diffraction and interference patterns, are basically the same thing. So you should start to see that is that the first two lessons in this topic are the same, and the last two are almost the same. So it makes it really nice as a final topic that we're going to be constantly reviewing this stuff. So these equations are still going to hold true from before. Like I said, the only real difference is the sign convention. Now, you could use this equation for a diverging lens. This is just a general form of this. However, the one thing that I want to point out is if you use this equation, you are not worrying about the sign convention. This equation is already taking into account sign convention. However, you do want to be careful of this. In fact, I would probably advise not using this once we start dealing with combination lenses, because you'll find out then that this equation may not hold true. So I would stick with this more general equation and remembering these sign conventions. All right. So you're going to do the same thing you did last time. Uh, I know I drew a ray diagram, but I would recommend you trying to draw one yourself. So draw it, and then you can pause the video, work on this yourself, and we'll go over it in a second. All right. So I'll do this. I know there's already a ray diagram on there, but I'm going to do one real quick. So I have my object. I'm going to draw my lines. So I'm going to draw the same type of lines I did before. I do parallel, and then through the focal point. And then the next one, I do through the focal point, and then parallel. And then the last one is going to be through the center of this. Wow, that was perfect setup. And what we're going to end up getting, there it is an inverted arrow. So basically, as we probably could have guessed, we should end up getting an image that has a negative height, inverted, and it should have a positive distance. As far as what that distance is, I'm not really too sure. I'm not even going to attempt to guess this time. So to figure out the position and the size, we'll use the equations. So we'll use our mirror equation or the lens equation, whatever you want to call it. Plug our numbers in. What we are going to want to do is just make sure that they all have the same unit. So convert this into 5 centimeters, this into 100 centimeters. When we do that, we end up getting that the image distance is 5.26 centimeters. So it's going to be very close to this lens. And then when we do the magnification, when we plug our numbers in, we get a negative magnification, uh, which ends up giving us a slightly smaller image formed. All right, and that's basically it. And again, that matches what we expect from our ray diagram. All right, here's another one. Again, I recommend trying to draw out the diagram first. Try not to look at the diagram, um, and work on this yourself. You can pause the video. We'll go over it in a second. All right. So just like before, we had this converging lens. It turns out that as we bring the object in between the focal point, it ends up kind of not converging like we expect. So if I do the same thing, so I'm going to take my arrow, I'm going to place it here in between the lens and the focal point. I end up doing the same thing. I do a parallel line that goes through the focal point. I can do a line that goes through the center. I'll extend it out a little bit on this side. And then we'll have a point that goes a little hard to draw this, goes towards the focal point. If I extended this, I should probably clean this up a little bit. There we go. Goes to the focal point, and then would have gone parallel like that. None of these work, so what I have to do is I have to then backtrack everything. I backtrack that refracted line. I backtrack this red line. And it turns out, look at that. All the lines pretty much cross at this segment right here. So we end up getting our image formed on this side, the same side that this object was placed. So I should end up noting that I get a larger image, a positive image, and it should be negative distance. So these are going to be my 3 checks. And again, we could see it in this diagram that they showed us. All right, so we plug our numbers in, and then again we get our negative image distance. We take the magnification equation, plug our numbers in, and we end up getting a positive 3. So it ends up being 3 times bigger than what we get. This is pretty much how a lot of magnifying glasses work, where they'll end up making the image very big by making sure that the lens has a far enough focal point that the object will pretty much always be inside of that, inside the focal point distance. All right. Now, I do want to actually point out one thing, because I know we talked about, virtual images and real images with the mirrors. A similar thing could be used here. Just like before, if the image distance is negative, it's usually considered a virtual image. Again, the reason why that is a real image is when you can place a piece of paper there and have the image formed at that location. Now, with the mirrors, it's a little bit tougher to see this, but with lenses, it's extremely easy. If we have an object on the left side and light travels through the lens, it's going to form an image on the right side. We could put a piece of paper there and clearly get the image on there. That's, if you look in the beginning of this slide, you would have seen that with one of the letters, the letter F. However, if I try the same thing here, if I place a piece of paper on this side of the lens, technically the image or the object would end up blocking this. Like, it would block all the light coming from this. So it wouldn't actually create anything. Again, the only reason why we see an image here is mainly because our eyes get deceived and think that the light is coming from that location. All right, so here's another one. You can pause the video, work on this yourself, and we'll go over in a second. All right, so I want to again try to practice going over how these lenses, how the ray tracing works. So here we have an object placed outside of the focal point. So I just want to make sure where I place it. As long as it's outside, that's all that matters. So we get 1 point goes parallel. Now it's not going to converge to the focal point. Instead, it's going to diverge as if it came from the focal point. So I'll just do this, and then I'll do that. Or you know what, I'll actually keep this extended out. And again, I'll erase this, make this dotted. All right, so then the next one is going to go. The good thing about I always like this through the center because that one's pretty much always going to be like that regardless of which type of lens it is. So we have this one, and then the next one is going to go through the focal point, oh, through the focal point, and then parallel. Now, once again, we're not going through this focal point because this isn't a converging lens. We're going to go through this focal point. So, uh, one thing to kind of keep in mind is that when we're doing this, that we're pretty much uh, almost doing the opposite of what you would normally do for the converging lens. So if we would have normally went through this focal point, we go through this one now. If we would normally have gone straight to this focal point, we're going to go straight and go through this focal point. So just keep that in mind. All right, and here we go. That's close enough. Erase some of these because these are my backtracked lines. Remember, these aren't actual lines. And then our image created is going to be right here where all three of these lines converge. So we're going to have a number that is smaller than our focal point, probably, but it's going to be positive and it's going to have a negative image distance. All right. So when we plug our numbers in, again, making sure that we now make the focal length negative because of the fact that this is a diverging lens. We get that the object distance is actually 100 centimeters. So this time we're actually doing something different. We're looking for the object distance rather than the image distance. We plug our other numbers into the magnification and we get 0.2. So this is actually why I kind of made the comment about the real and virtual images, because they may sometimes throw this in there and expect you to realize that the image distance has to be made negative 20 rather than just straight up telling you negative 20. They won't always give you the diagram. All right. Now, like I said, the more important thing that we're going to talk about are the combination lenses. This is really where the crux of this entire thing is going to lead to. Unlike before, it was kind of tough to, I mean, you could always have multiple mirrors, but that kind of made everything a little bit messier. But with lenses, we can do this very nice and easily. Now, with a combination lens, what ends up happening is that we'll end up creating an image from the first lens that will end up acting as the object for the second lens. Now, some other things that we're going to find out is that the total magnification of the entire combination will actually end up being the product of the separate magnifications. So each lens you have, the magnification is just going to be multiplied by that one. And we'll show how it's derived a little bit later. Uh, and oh, so here is pretty interesting. It says, and this is why I made my little caveat mention before, even if the second light second lens intercepts the light before the image is formed, it still ends up working. What that means is that if you have two lenses right next to each other, so we have uh, this lens, then another lens right next to it, um, if the image is actually going to be formed on this side of the second lens, well, then we could still do a lot of the same things. It's just that we end up having to take into account the sign convention because it's not coming from where the light's coming from. So keep that in mind. So what we end up having is pretty much a similar thing that we would normally do. Now, the one thing that I want to point out here is that you'll notice that they do a lot more extra lines, lines that you wouldn't normally have to do. Um, this is coming from the fact that they want to show you how some of the lines that created this will now form the final image. Like for example, they add in this one, the going through the center. The going through the center one is going to go through until it hits here, and then it's gonna end up going uh, through a refraction in order to create that new image. Now, you would never actually create this line, but it's just showing you that this line will create this. This is how it would look. Same thing here. They added in this extra line to kind of get a through the center moment. So they kind of changed things around. I would be completely fine if you just did your three lines or even two lines, parallel, focal, focal, parallel through the center. And then once they cross, you do those three lines again, focal point, parallel, parallel to the focal point, and then through the center. So just keep that in mind that this is a little bit more complex of a ray diagram than what you'd be expected to do. But this also plays into how we end up having this image formed here, and this image now becomes the object of the second lens. So you'll have to take into account the spacing of this lens in order to actually answer these questions. All right, so keep this in mind. All right, so you can work on this video, pause it. Don't forget to do a quick little diagram as best you can. Try to like guesstimate the focal points and all that, and we'll go over this in a second. All right, so I'll try and quickly make a combination lens. So what we're going to have is something that looks like, oh, something that looks like, I'll say it's like this. I'll get rid of this one. Alright, let me check some of the numbers. 20 and 25, and they're 80 apart. 20, 25, 80. Sure, that should work out. About. Where is this? And it's going to be placed over here. Make it a little smaller. So the lines are going to be done like this. So we go, are they both converging? Just want to double check that. Yeah, two converging lenses. So we have a line that goes parallel through the first focal point. Then we have through the center. Oh, wow. Looks like I stopped the line at the perfect spot. And then through the focal point. And then, okay, maybe not perfect. And I guess this one goes up a bit. All right, so my image is going to be formed right here. And then from here, I'm going to do essentially the same thing. I'm going to do another set of lines. I'm going to go parallel through the focal point. I'm going to go through the center. I know they don't cross, but they will cross eventually. And then through the focal point, and then parallel. If I extend this out, it's most likely going to cross somewhere around here, I would say. Say right there. So what we're going to end up getting is an image that is created on the right side of the lenses. So we should end up getting a positive distance for our final image. And its final height should end up being positive, and possibly bigger than what we started with. Again, not too sure. It's a little bit tough since some of my lines weren't really drawn properly. So we'll see. All right. So what we're going to do is do our equation first to figure out where's the final image being created, or where the initial image is created. So we plug our numbers in and we get 30 centimeters as the image distance. So if this initial image is formed 30 centimeters from the lens, and the two lenses are 80 centimeters apart, what that it's going to tell me is that the object to the its distance from the second mirror as an object is going to be 50 centimeters away. From there, I can do the equation again to find the final image distance, and we get that it lands 50 centimeters to the right of the second lens. A lot of times, you're going to want to try to add in that little indication of where is the image being formed compared to which lens, because again, we have two lenses now. So realistically, this should say 50 centimeters to the right of the second lens. Now for the combination, for the magnification, well, we just find the individual magnifications. The first lens went from an image distance of 30 and an object distance of 60, had a negative 0.5. Makes sense. We ended up getting a slightly smaller arrow with an inverted direction. We do it for the second lens and get negative 1. When we multiply them, we get that it's positive 0.5. So I did get the positive part. Didn't really get the whole smaller part, but that, like I said, is mostly attributed to the fact that this arrow is really close compared to what it should be. This should be a little bit further away from this lens, and this should be a little bit further away, and all these other things. Again, with these drawings, unless you're being completely to scale, doing sketches will not really give you very accurate information, but it will give you a good idea of where along the on which side of the lens is it going to land, and is it going to be landing upright or inverted. All right, here's the next question. You can work on this self, and we'll go over in a second. All right, so similar thing here. I'll try and make another one of these diagrams. So let me copy this real quick. I'll put it like that. Let me see some stuff. 13 and 16. All right. So that should be close enough at least. So we put a lens here, or an object here. Do the same thing. Draw. Now, again, this might not be super accurate since I wasn't, I'm just working on paint. So forgive me for any, if I end up getting a image that isn't formed the right way as it should. But when I draw my 3 lines, I should end up getting, all right, that one's actually forms a little bit better. So we get an inverted image here. Okay. Do the same thing. So it looks like I should be getting a similar result compared to what I got last time. So I'm not too sure if, like I said, maybe I might have made a mistake with the spacing of these two lenses compared to the focal lengths that I created. That actually is something that I probably should point out, is that currently the focal lengths that I've drawn are exactly the same for these two lenses. And that is going to create an image somewhere around here. So this is kind of what I'm getting. Again, something very similar to what I got last time. Typically, you'd want to make sure that you kind of, you don't need to have these diagrams drawn perfectly to scale, but you do want them roughly in line with each other. Like when I was looking at this, I was trying to make sure that these two focal points weren't overlapping. So, this one has a focal point of 13 centimeters, this has a focal point of 16 centimeters. So they are going to be, they're not going to have an overlapping case, because then what I did here wouldn't make sense if this was the second lens's focal point. But that's what I end up getting. I pretty much get a similar result from last time, so we'll see if that works out. It turns out that thankfully that's exactly what we ended up getting. We ended up getting an image over here, though they got a very small image while my image is still extremely large. However, a lot of that could be, if you notice the way my drawing is, the focal points are really far away from these lenses compared to the object distance and the separation. But if you notice here, these focal lengths are actually much closer to the lenses compared to these spacings. So again, could be caused by that. Usually when I do this on paper, I would get a much better ray diagram that's actually closer to what you expect. But we end up doing the same thing here. We're going to get, we do the lens equation for the first lens to get that the image distance is 20 centimeters from the first lens. And then because of the 56 separation, we can figure out that it's an object distance of 35 centimeters to the second. Use the lens equation again to find that the final image distance is a little bit under 29 centimeters to the right of that lens. Then for the relative size part, we take the two equations for the magnification, multiply them, and we end up getting 0.46. So we end up getting that it's upright and smaller than our original object, something that for some reason my diagrams aren't really getting too well. All right, so that's going to be it for this one for now. When we come back for the second part, there will be a few more combination questions to work on, so just keep that in mind. If you have any questions, please let me know. Otherwise, I'll see you later.